So let us solve this problem, simple problem, because it is a simply supported beam of redundant 0. It is a structure with no indeterminacy. Even though if you want to make the structure to mechanism, we need only one hinge because R is equal to 0. The number of hinges required, the formula is R plus 1. Here there is no redundant. 0 plus 1, only one hinge is needed. It is always under the load. Here the load is a uniformly distributed load. So we can select the midsection. To form one node. So this is node. So if you understand the angle of inclination of this deflected shape, this is the deflection delta. The load is here. Delta. If you draw a horizontal line, this theta will be available here. This theta will be available here. So totally under this point 2 MP, 2 theta is available. Totally 2 theta is available at this point. So now our concept is to equate internal work done to the external work done. Internal work done to the external work done. External work done implies with W, that is W into delta. External work done implies with the external load and the deflection. Internal work done is implied with moment of resistance and the rotation. If you multiply with moment with rotation, it will give a work done. Or else, if you multiply a load with deflection, it can also give the work done. So here we have to count how many number of moment of rotation is possible. Here the number of rotation under the point load is 2 theta. So I can write here MP into 2 theta. And how we can calculate delta? You take 1/2 of the triangle. The total span is 6 meter. So here it is 3 meter. Here it is theta. So if you write tan theta equation, it is delta by 3. And simplify tan theta with theta. So theta equal to delta by 3. Where delta equal to 3 theta. So delta we can put 3 theta. W is normally a point load. If it is a UDL, we should consider the area of loading diagram. So the loading magnitude is 25. Area of this diagram is equal to half. B is 6 and H is the delta. Half B into H. So it is 2 to 5 theta. External work done. Internal work done is equal to 2 MP theta. So MP is equal to 2 to 5 by 2 into theta by theta. So 2 to 5 is equal to 112.5 kilonewton meter. So the plastic moment of resistance of this section is equal to 112.5 kilonewton meter. So for example, if in the reinforced concrete section we are calculating the area of reinforcement for the particular moment. Likewise, here the plastic moment of resistance is equal to 112.5 kilonewton meter. So we have to select the I section. So I am using the theorem of simple bending, that is MP equal to sigma y into ZP. So ZP is equal to MP by sigma y. MP we know 112.5 into 10 power 6 Newton mm. divided by sigma y is given, so 250. It will give the plastic moment sectional modulus 4.5 into 10 power 5 mm cube. For the shape factor, Zp by Z for the I section is equal to 1.15, which is already we have learned the derivation for the I section 1.15. So I am using the shape factor value 1.15. If it is not given in the problem, you can assume the shape factor. The definite value of the shape factor you can assume. So Z equal to Zp by 1.15. So 4.5 into 10 power 5 divided by 1.15. So the Z value required sectional modulus is equal to 391.30 into 10 power 3 mm cube. So for this corresponding sectional modulus, we can choose an I section ISLB, referring your steel table ISLB 275 at 330 Newton per meter can be chosen for the I section, or otherwise you can select any other corresponding section with the sectional modulus of 391.30. So this is one of the very simple problem.